All right, so welcome to M5, and welcome to the third talk in our series of departmental honors senior thesis talks. Today we're very happy to have Michael McKinley here, and he's got all kinds of great things to explain. And let's see, as far as upcoming events, next Tuesday, Alex is back. Alex Trafonis will be back explaining Facebook application. So he and his team in the SDP have created a Facebook application using the Facebook API, and he's going to take that apart and show how one would create one's own Facebook application. All right, Michael, thank you.
Thank you.
Welcome.
So I'm Michael McKinley. I'm a graduating senior ComCall student in the Mechanical Engineering Department. And I think after last week I was, the example set forth to bring your own posse was a good choice. So I tried to do that myself, but unfortunately I don't think most of them got past the EE bouncers at the door. So anyway, today I'll be talking about how we use some interesting properties of polymers to create text on extruded plastic. So as shown by the title here, that's let's see. Oh, come on. Get some issues with the mouse going on here. All right. So, kind of the basis of my project is the production of sharkskin. Sharkskin is a micro ridge-like structure produced on an extruded surface. And this comes about as a result of an instability that occurs at the exit plane of a die. So you can see here in this diagram, we've got a bulk flow of plastic in this region. It's being extruded through a die face, and due to a temperature gradient, the die exit plane being a lower temperature than the bulk flow, we get a stress singularity. And so this happens as a result of a no-slip boundary and the bulk extrudate rapidly accelerating to the plug flow of our polymer. So as a result, if this temperature gradient is too high, we get some pretty severe ridge-like structures, as shown in this image here. And these can be, up to about 100 micrometers in scale. In industry, this is a big problem. So you don't want your extruded plastic to have a surface texture like this. But we're actually using this to our advantage to produce some interesting textures. So a little bit of background. This project came about 5 years ago, I believe, by a student named Eric Miller, who was getting his master's degree over in mechanical engineering. And he was working on a single gradient sharkskin project. And so basically we have here is a schematic of his die. So we're able to produce a temperature gradient between the main heating zone of our extruder and that output plane of our die. And in doing so, we can create a single extrudate difference in sharkskin in one dimension. So we can see here we got cylindrical sharkskin of varying degrees, and the difference in sharkskin magnitude is created by difference in temperature gradient between your bulk flow and your output plane. So moving forward, the next step is to say, well, okay, we can do that in one dimension. How about two? So we got two different gradients going on here on either side of a square die, this stainless steel looking chunk, and where you've got two heaters, two different heating implements, and it's the same technique more or less. So I'm expanding further and saying, well, how small can we actually get this, and how tight can we pack these features on a single extrudate plane? So we got some images here of my design. It's a similar interfaces with the same extruder barrel as before, so I don't have to deal with that problem. But we're looking at a die with three heater pins, and each heater pin is a temperature-controlled loop. And we'll talk more about that later. But you can see here so these are brass heater pins separated by an insulator layer, and in a main heater block which we can maintain at a temperature. So if you look at this drawing here, we can see as this extrudate is coming out, the last surface in contact is this temperature-controlled pin. And so right in these regions, we can control that surface texture and hopefully create some interesting designs, well in this case letters is our proof of concept. So here's an image of the extruder itself. We've got a main temperature controlled barrel. So this is aluminum obviously, and we've got heater bands in 3 places. And that's used, controlled by an industrial heater controller. And then we've got, so that's kept at around, say, 150 C. We've got high pressure line nitrogen tank behind here. You can see through this guy here. And that's rated for 2,000 PSI. So it's some interesting stuff. Here's our pellets that we have inside. Standard, it's more or less hot glue. It's run-of-the-mill plastic. And then here's another image of our extruder. So you can see if we get that cutaway. So our extrudate surface is no longer in contact with our die as we're exiting our die head. And a final image here, we can see our heater pins and all the controls, well, the feedback part necessary to control our temperature. So we've got 30 gauge nichrome wire wrapped around our heater pins, and buried inside that head we have some really small temperature sensors. This is a case, these are RTDs. I'm actually using LM35s, which are a temperature IC. So they're approximately the same scale. So I guess the LM35s are actually really nice because they interface with the Arduino without an issue at all. And that'll be part of my project later here. So you can see those pins are assembled and then epoxied in place. And our epoxy is our insulation barrier between each heater pin, each heater element. And one of the problems with the design is that you've got to actually machine these things in a specific order. So if you have a problem down the line, you've got to start over due to the limitations of our machining. So this design was pretty much pushing the limits of what we could do with the tools and techniques that we have available. So I mean, obviously we're dealing with high pressures here, so safety's got to be our top concern, right? At least top 3. Yeah, so I don't really think any of that would do me any good if it did let loose, but it felt better, and so it did. And the non-Newtonian fluid dynamics lab actually looks at Kevlar as one of their projects. So they happen to have a Kevlar vest and helmet sitting around. It's like, well, I might as well put it to use. If something happened and I wasn't wearing that, that'd be a problem. So anyway, so it works. And that's the cool part. You can see here we get a pretty large difference in texture between our large surface ridges around the 100 micrometer scale here and our smooth surface here. And this is a coloration behind, so you can actually see the difference a little better. And that's just a kind of a gross start point with my design to see how well it was functioning. But then we get into the fun stuff. So we do an initial system identification on my die, so I could make a math model of it and simulate. So this is a regression-based system identification technique. Pretty simple stuff, and fit first order, second order system to it, so I can get an accurate model later on. And then obviously we've got 3 heater pins. So if we want to print text, we need a specialized font. So this is my patented trademarked 3-pin heater font, and you can download it from my website if you want to type your papers in it. It's a true type font. And you know, naturally, any of you got here late, we got start over again here. So we're got a comm call talk. I'm Michael McKinley. It's legible, you know. And since this is looks like Space Invaders, it's endorsed by Sun Ra, the spaceman himself, and his orchestra. Space is the place, right? So all fooling aside, we've got to do some math here to make sure we know what's going on. So I did a 1.5 dimensional finite difference approximation for my temperature gradient throughout, and that's 1.5 in that it's we've got a 1-dimensional finite difference approximation, and then it's swept over an area just to get our idea of what's happening over time. Because all we really care about is that last interface with plastic. So the important things to note here is we've got our Fourier number, which is really the important part, and that's comprised of our thermal diffusivity of our insulation material.